So hello class, it's Professor Hanna. Have a brief lecture here. This is your first one on Chapter 10. We'll look at inventory management, take an overview of the material in the chapter, and look at a particular model we use to manage inventory. From an overview perspective, the things we'll be looking at have to do with why we would want to have inventories and what they do for us, positive aspects, and then reasons we might like to have less. We'll look at some of the tactics we use to manage inventories in a supply chain and talk about ABC analysis. This form of Pareto analysis basically sets importance levels for inventory items, which helps us to know what sorts of policies we might use to manage those. Finally, we'll look at Q model. So Q model is a type of independent demand inventory system or model that we use to decide how much we need to order and when we should place the order. A Q model will optimize the amount we order. So it's something we would do for really important inventory items that we keep track of on a regular basis. We might even say we have a continuous review policy for them. So if we know how much to order, the optimal quantity, the next question would be when we place the order. We'll call that the reorder point. And basically it's the level of inventory that we would want to have so that when we place the order, we're sufficiently confident we'll get it in before we stock out. These are mathematical models. Some people call them stochastic models. So the Q model is one of the simplest and most commonly used to describe inventory models in production systems or operating systems. What you see here is a real common picture. It's called an input-output model having to do with inventory. Some people just call it a bathtub model. And the point of it is that inventory is something that relates to both our input and output rates. So if we can ship more, we'll have more than we bring in, then we'll have reduced inventory. And if we bring in more than we ship, we will have increased inventory. So if we pay attention just to input and output, a lot of times we can understand whether or not inventories are growing in our system and whether the operating system is working like we would hope that it would be. So when we think about inventory, in recent years, there's been a lot of emphasis on becoming more lean. And part of the reason for that emphasis is that we can really kind of improve a lot of characteristics in operations if we are more lean. So if we have inventory sitting around and a problem arises, and for example, we get a bad part that we're trying to use in assembly, then we can just pick up a piece of inventory that's standing by, use that, put aside the bad part, and we never get to the idea that we really need to fix the problem that created the bad part to start with. And so that's one of the reasons that in today's world we're really kind of oriented toward having a lot less inventory, and we want to have small inventories. Is this issue that inventory carries baggage with it, sometimes in the form of a reduced or eliminated quality feedback loop. But other things that come along with inventory is the cost of holding it. So, we got money tied up in that. It could be used in other ways. We probably also, if we're holding it, we've got to have shelving space. That space has to be maintained in some way in a facility. And so it can be expensive to hold inventory. If we're holding inventory, we may have to handle it. We may have to move it around from time to time. We may have to pay property taxes on it, depending on the environment where we're operating. We may wish to insure that inventory. It could be stolen, it could become obsolete, it could deteriorate over time. So, a lot of reasons why we want to be careful about having too much inventory, and so these are pressures for smaller inventories. At the same time, if we have more inventory, there are things that we can do differently. So, for example, we can provide customers with better service. Every customer loves to be able to walk into a facility, see the thing that they want to buy, and take it home right now. It's rare that you or I would go, let's say, to a car dealership and just buy a car, saying, well, maybe it'll be a nice car when I get to see an actual model of it, but I'll go ahead and buy it. No, we'd like to see it and we'd like to take it home. If it costs a lot of money to set up to produce something, or takes a lot of time to set up to produce something, or if there's a lot of paperwork involved in buying whatever it is we're talking about, then what we might want to do is buy a lot of that or make a lot of that item at the same time. And of course, if we do that, then we're going to have larger inventories. Lots of times we like to have inventory to make sure that we keep equipment operating or labor operating. If we've got for example, a paper mill, a continuous flow process of some kind that's set up to run 24/7, it's a very capital intensive process. We really don't want that equipment, that process, to sit idle. And so we'll make sure that we have large supplies of raw materials. In our part of the country, oftentimes I drive by it's a lumber operation where they chip pine, and they also cut certain dimensional lumber. Well, that thing you'll see, especially when the winter is coming on, and it may be difficult to get in and out of the woods because of a lot of rain and wet soil, boggy conditions. Then you'll see, as winter comes on, piles and piles of this lumber that's ready to be processed. So making sure we keep work for labor and equipment on hand is a reason why we may choose to have higher inventories. Transportation costs, somewhat like ordering cost. So if we can get a discount by shipping a full truckload instead of less than truckload or something of that nature, we may choose to have bigger inventories. Finally, sometimes suppliers will give us quantity discounts, and that would be another reason to go ahead and buy more, and potentially we would have to evaluate the benefit of the discount over and above the cost of holding the excess inventory, but that might be a reason to have higher inventories. So there's kind of trade-offs involved in inventories, and you're going to see that as we work through this chapter. You're going to see mathematical models that help us to play that trade-off and find the right balance in terms of the size of inventories that we'll be carrying. So you're familiar probably with the way accountants talk about inventory, and they classify inventory in terms of raw materials, work in process, and finished goods. If you look at a balance sheet for a firm or something of that nature, you may see one line for inventory, or it's possible as you dig down into assets that you may see these different types of inventories. So, in a manufacturing company, we may have a finished goods warehouse where we have these inventories. This is sort of an example of a company that makes hardware, I guess. But in the manufacturing plant, of course, we would have work in process and potentially some raw materials. As you look at this, you'll see a couple of things. And the first thing you're going to see is that between the retailer and a distribution center, and maybe even the manufacturing plant, there's some redundancy in the inventory of finished goods. And it may be possible through supply chain strategies for us to reduce the need for this redundancy. The other thing that you'll notice is that even though we're thinking about this inventory in this slide from an accounting perspective of raw material, work in process, finished goods, there's a relationship between the inventories. So it's real easy to see that the finished goods are made up of what was at one time work in process. I mean, that's obvious, it's a trite statement. But what it means is that when we're managing our work in process inventory and potentially our raw materials, the way that we do it is going to be reflected in the inventories of finished goods we have. Another way to say that is we don't need the parts unless we're going to make the product. And so the product here, the Le Bolt package, is what we would call the independent demand item, that finished good in a package. And so we don't need the packages and we don't need the bolts unless we have a requirement for the finished goods. So if we want to decide how much of that thing that we sell we need, then we're going to have to forecast the demand for that. And we're going to have to decide how much we're going to have and when. So, that finished good is something that the plans around that are really driven by demand forecasts. And we all know if we're forecasting something, there's uncertainty associated with that. And so the way that we handle this finished goods inventory, we call it independent demand inventory because it has to be forecast. The way that we handle that has to take into account the uncertainty that is present in our forecasting. By contrast, the bolts and the packages that make up that finished good would have dependent demand. And by that we mean unless we've got to assemble a package of the finished good, we don't need a bolt, we don't need a nut, and we don't need a package. So we can actually calculate when we need bolts and how many of them we need, when we need nuts and how many of them we need, and when we need packages and how many of them we need. So we don't have to forecast the demand for those dependent demand items. We simply need to calculate it on the basis of what our plans are for the independent demand items. So most of our interaction with customers happens over independent demand items, and that's really where the focus is in this chapter. And in later chapters we'll move to, and really it's later in the course, we'll move to a brief discussion of how we might handle dependent demand items. But that's a different type of inventory from an operational perspective and from a decision-making perspective. So we've talked about inventory kind of from the accounting perspective and began to talk about it operationally on the last slide, where, we said, well, there's work in process, there's raw materials, there's finished goods. From an operational perspective, we classify inventories perhaps in a slightly different way. This isn't something that you'll see on a balance sheet, but it is something that's important from an operational decision-making perspective. So 4 types that are identified by your book. These are not the only ways we refer to inventory in operations, but these are common considerations. So cycle inventory, safety stock inventory, anticipation inventory, and pipeline inventory. Let's talk about what these are, and also we'll talk about some strategies around not having too much of what these are. So, cycle inventory is simply inventory that is being used and replaced on a regular basis. So this is kind of like when I place an order for coffee from Amazon, I know that that coffee can that I order is going to last me 2 weeks. And so in 2 more weeks, I'll order another can. And the cycle inventory is whatever's in that can at any given point in time. So it's what I have on hand to use in the regular cycle of handling this item. Safety stock inventory is the extra can that I have in my pantry. So the reason I have that safety stock inventory is in case, let's say, there's a strike at Amazon.com, or maybe there's a bad weather event and I've ordered it and it's supposed to come by Monday morning, but it doesn't come by Monday morning. And so, well, good thing I have that extra can sitting in the pantry. I'll pull that out and use it. And when that new can comes, I'll just put it back there. And so I'll always have that safety stock. That safety stock is there throughout the cycle, and I really hope to never have to use it, but if I need to, it's there. I don't run out of my coffee. So anticipation inventory is something that we kind of use when demand is really variable. You might think about, let's say, a company that makes and stuffs Easter baskets. So they mold the baskets with an injection molding thing, plastic, or maybe they buy some wicker baskets and bamboo baskets, that kind of thing. And then they put the Easter grass in it or whatever else it is, and the candy that goes in there. Well, you know, they're going to be really busy up in the months of, let's say, December and January and February while they're preparing the orders for major retailers like Walmart and Walgreens and CVS and whoever else sells this kind of thing. Your grocery stores too, I suppose. So, but once they've shipped these things, say a couple months before Easter or whenever it is that their contract calls for delivery, they don't have much to do. I mean, they're done. So it's a real uneven demand pattern that they're responding to. And if they had, for example, some anticipation inventory, the idea would be that instead of working real hard in, let's say, December and January to complete their orders, they could work a little less hard, let's say from September to January. And they build up inventory as they're going along, and then they can deliver a whole lot at once when demand is really high. So that's the idea. Anticipation inventory, you see something coming. You see a big surge in demand, and so you go ahead and get working on it, and you're left holding inventory until that surge actually materializes. Pipeline inventory is simply inventory that's generally in a production setting we would call work in process, and it's simply necessary in order to operate your process. If you think about an assembly line, then you need something to work on at every station on that assembly line. We'd call it pipeline inventory. If you think about the Alaska pipeline, goes from, I guess it's the northernmost area in Alaska down to Prudhoe Bay in southern Alaska. It's hundreds of miles of, I think, like a 12-foot diameter pipe. So there's a lot of oil in that pipeline. And the same thing's true in a lot of production settings. If there are a lot of steps in the production process, you're going to have a lot of value tied up in inventory that just has to be there because you have to have something that you're working on at each workstation. So operationally, we have these types of inventory, and we have a mindset that we want to be using inventory in the right ways, playing these trade-offs between large and small inventory in an appropriate way. So to reduce cycle inventory, what we would need to do is reduce the lot size. I talked about the can of coffee. If I wanted to have less inventory in my closet, then I could just order small cans, maybe 2 days worth, and order it every other day instead of ordering a big can and getting it every other week. So as a result, the cycle would be shorter and the cycle inventory would be smaller. If I can increase the repeatability in terms of the way I produce in a manufacturing setting, or just get on an automated delivery system in a purchasing setting, then potentially I'm more comfortable with shorter cycles and smaller lots, and that enables me to reduce the cycle inventory. We'll see a lot about that. We'll talk about that in some depth when we talk about lean and the just-in-time production system toward the end of the class. So safety stock inventory is there to cover me in the case of uncertainty. Remember I said I keep that in that second can in the closet just in case there's a weather event or a strike or some reason, some unforeseen reason that my shipment from Amazon is not going to come at the right time. So if I can reduce the uncertainty that I'm facing in any particular way, perhaps by ordering something that is stocked at a warehouse that Amazon has closer to my house rather than ordering something that's stocked in Seattle, which is all the way across the country from where I live, then there's less uncertainty. The lead time is shorter to get the shipment that I've ordered, and as a result, then perhaps I don't need as much safety stock. And actually, in a manufacturing setting, if we have extra capacity, then maybe we don't need to protect ourselves from a uncertainty in terms of whether or not what we're making will be ready in time to use it. So if we have extra capacity, we can put more resources to that situation if we're getting behind, and we don't need the safety stock. Instead, I suppose you could say, we have safety capacity. In terms of anticipation inventory, a lot of times what people say is what we could do in order to keep the production rate more level is add products. I gave the example of the Easter basket. So if I injection mold these baskets to have them filled, and I build up anticipation inventory because I want to start in September instead of starting in December, well, if instead of just doing Easter baskets, I was also doing these Halloween jack-o'-lanterns and injection molding them. And also I was doing something like for sale in the summer beach buckets, that we use, and the little shovels and things like that we use on the beach. And maybe there were other seasonal products that I could injection mold. Then I could keep my injection molding equipment operating at a relatively steady rate that's high enough that I don't have to build the anticipation demand inventory ahead of time. I just, I have enough capacity to build it in the period where that product is used. So Adding new products with different demand cycles enables me to be in a position to use a lot of capacity in a short period of time on any given product of that sort. Also, marketing strategies like pricing plans and promotional campaigns would enable us to move demand forward. So now the retailer takes delivery of the Easter baskets in, let's say, December instead of taking delivery in, let's say, February. And so that saves me the need to hold the inventory. The inventory is in the supply chain, but it's not on my balance sheet. And so these off-season promotional campaigns and pricing plans, those kinds of things can help us reduce the anticipation inventory that we're carrying. Pipeline inventory is, in a way, it's a fact of life, but if we can improve our process so that the pipeline is shorter, perhaps reducing lead times, perhaps having more responsive suppliers or more efficient, more rapid cycle logistical system. These kinds of things may be helpful in a supply chain to reduce the amount of inventory that's in the pipeline. So that's sort of a description of inventory from an accounting perspective and then from an operations perspective. Let's change gears and start talking about how we might use models to help us make decisions about, actually we're going to focus on independent demand inventory items in the rest of the chapter. So one of the tools that's really useful in terms of managing inventories from an operational perspective is called ABC analysis. It's actually Pareto analysis. You've seen Pareto analysis in a lot of contexts. Probably saw it in your marketing class. They probably said 80% of the sales come from 20% of the customers or something like that. So you're going to focus on the customers that are high value customers. In quality, we said 80% of the problems come from 20% of the causes. So you're going to focus your attention on the causes that are really, the big levers for improvement. And with ABC analysis, we're starting to say something similar. We're going to say, there are inventory items that are really, really, really important. We'll call them Class A items. Maybe 80% of our dollar volume in sales comes from these few items, maybe 20% of them, roughly. So the way that we handle those should probably be different and make decisions about those should probably be different than the way we make decisions about and handle Class B items, which, they're important inventory items, but they're not the most important, and Class C items, which would be our least important items. So you've seen this actually in a lot of settings. Most likely, if you go to a retail establishment, or let's just pick something. Let's say you go into an electronics store, and you're probably going to see some things that are in a display case. They're locked up. I'm guessing those things might be expensive. And, they're on display. They want them on display, but they don't want you just handling them and maybe putting them in your pocket and walking away. You could say that because they have those under lock and key, at every moment of every day, they know exactly how much of those items that they have on hand. So Class A items are those kinds of things that you're willing to have a constant knowledge of. How much do we have? And we could say you have a perpetual inventory record on those items. Probably, if you start to run out of a Class A item, you're going to do whatever you need to get more of that in. We could think about Class A items in terms of, let's say, Taco Bell. You know, it wouldn't be cool if Taco Bell didn't have any taco shells in a particular establishment. So at a Taco Bell, the taco shell, that's the Class A item. Maybe you love the way that sounds. I went to Taco Bell, they had a taco shell. That's their Class A item. There are others. They probably want to make sure they always have the meat for the taco on hand, the lettuce and so on. And they probably are watching their stocks on those things and are not going to run any risk of running out. And if it starts to look like they might, they're going to do something about it right now for that one item. It's just worth it. So Class B items, they're important, but they don't require that level of scrutiny and maintenance. So, for example, back to the electronics store, when you walk in, these are items probably that are on display, but they're not necessarily locked down or in a display case locked up. And, so they're things that the company's paying close attention to, but they're not going to keep a perpetual inventory record on these things. So, even you might have seen people in the grocery store as you're getting your groceries who are sort of walking down the aisle with a little scanner. They're looking at the shelf and they're saying, I wonder if we need some more of that. They'll look at it and say, yeah, I guess we need some more. So they'll scan the barcode and they'll enter a number for how many to put on the next truck that happens to be coming this way. So that's Class B items. At Taco Bell, that might be, Diet Pepsi syrup for their drink machine. At the electronics store, it might be, batteries for remote control. Or it might be at the electronics store, let's pick something, a little more. It might be, if they sell microwaves, it might be microwaves or toaster ovens or things of that nature. So Class C items then are items that we carry, and there may be a lot of these. They may be on the shelf, they may not be on the shelf, that, we're maybe not too upset if we run out of these things. We may not be interested in jumping through a lot of hoops just to make sure we have them there. At the electronics store, it might be a replacement part, for a particular piece of equipment that we sold 6 or 8 years ago. We don't really sell anymore, but there's some customers that still happen to have it. And so they come in, they say, do you have this part? We might say, at one time we did, let me check in the back. And if it's not there in the back, we'll say, well, would you like us to order it for you? And if you're really in a rush, maybe you can check these other places. So that might be an example of what we'd call a Class C item. Maybe at Taco Bell, it's a toy and a kid's meal or something like that. So that's kind of what we're talking about. The key point is it's important for us to classify our inventory so that we can build inventory policies that are suitable to the item that we're managing. And that's what ABC analysis does for us. On the last slide, we said ABC analysis would help us set a policy for inventory items. So that being the case, we need to think about what that policy needs to give us. And what it needs to give us is an idea about how much we should order and when we should order the inventory item. At least from an operational perspective, that's what we want. So the question about how much may be answered by what we call a Q model, or an orientation toward quantity first in our decision making. We may want to optimize the order quantity. What we mean by that is figure out what quantity gives us the smallest or the minimal total annual cycle costs, the cost for holding and ordering that particular inventory item. That's something we would do with an A item. We would say, okay, here's what the optimal policy is for this one item. And so we'll implement the policy in that way. So let's spend a good bit of time here looking at what a Q model will look like. It's going to answer two questions. How much do we order? And when do we order? Then later on we'll look at a P model, which sort of answers the timing question first and makes the quantity conform to that. Here we order the quantity question first. That makes it a Q model. And we let the timing of orders conform to the quantity issue. So the most simple way to think about this is to think about a situation where we have known and constant demand, and we can order a lot in any size, and we're only going to look at holding and ordering costs, and we can make decisions for the one item on its own where lead time is known and there's not an issue of uncertainty in terms of when our order would show up. That's the basic scenario. If that's the scenario, our inventory levels are represented by this chart. I like to call it a sawtooth diagram, but that's just a Mark Hanna term. That's your professor's term. That's not some technical term. So anyway, you can see if we order Q units, when that order comes in, when we receive an order, we would have Q units on hand. If demand is constant, the amount we have on hand will decline in essentially a straight line. For example, if we order 100 units of this item at a time and we use 10 units a day, then the first day we'd have 100 when the order was received. A day later, 90, 80, 70, 60. 10 days later, we'd be down to 0. At that moment, we would receive another order. We'd be at 100. And so we have a 10-day cycle. And on every cycle, we would use 100 units. And our average inventory would be what we have at the very middle of the cycle, which is 50 units. So you can see that the slope of the line represents the demand rate in this scenario. So our annual holding cost in this scenario that you saw with the previous picture is simply whatever the average cycle inventory is times the cost to hold a unit for a year. Our annual ordering cost would just be the number of times we order per year times the cost to place an order. So our total inventory cost when we're thinking about our model would be whatever it costs to hold the inventory plus what it costs to order the inventory. And we'll just say in a manufacturing setting that ordering cost is actually a setup cost, setting up to produce the inventory. So oftentimes you'll see in the book or you'll hear me on the lecture referring to ordering costs or setup costs interchangeably. So when we think about those costs as they arise off of that sawtooth diagram, the holding cost, we said, is the amount that it costs to hold a unit for a year times the average inventory. Average inventory we saw was Q over 2. So this annual holding cost will simply be Q over 2 times H. And essentially that's a straight line. If Q is your horizontal axis variable and dollars is your vertical axis, then Q over 2 times H is the same thing as H over 2 times Q. So it's a straight line with a slope of H over 2. Ordering cost is the number of times you order in a year. Number of times you order in a year would be annual demand divided by the quantity that you order. So it's number of times you order in a year times the setup cost. So because Q is in the denominator when you're figuring the number of times you order per year, the bigger Q gets, the smaller your annual ordering cost is. That should be intuitively obvious. If you order every day, you're going to spend a lot ordering. If you order twice a year, you're not going to spend nearly as much. This is what we call a negative exponential function, so it has this sort of curving shape that's asymptotic to the horizontal axis. As the quantity gets big, the annual cost gets smaller. So the total cost is just the sum of the annual ordering cost and the annual holding cost. This is the total cycle inventory cost. To summarize and clarify, we just said the total cost for a cycle on an annual basis for cycle inventory is the holding cost plus the setup cost or the ordering cost. The annual holding cost plus the annual ordering cost. So the annual holding cost was Q over 2 times H, where Q is our lot size and H is the holding cost per unit per year. The annual ordering cost is D over Q times S. This is a capital D representing annual demand, and S is our setup cost per lot. Q again is the lot size. Let's look at an example. So a Museum of Natural History opened a gift shop. It operates 52 weeks a year. Their top-selling SKU is a bird feeder. Sales are 18 units a week, so annual sales would be 52 times 18. This thing is bought for $60 a unit. The cost of placing an order is $45. Holding cost is 25% of the feeder's value, so that would be 60 times 0.25 or $15. Management to start with chose a 390 unit lot size, and they want us to figure the annual cycle inventory cost of the policy using a 390 unit lot size, and then they want us to do it again with 468. So we'll just apply the formula that we had on the previous slide. Like we said on the last slide, annual demand will be the weekly demand of 18 units times 52 weeks a year, which will give us 936 units per year. The holding cost, as we mentioned on the last slide, is a quarter or 0.25 times a quarter of the price, or 0.25 times $60. There's our $15. So the total annual cycle inventory cost with an order of 390 at a time, if that's our lot size, our order quantity, then Q over 2, 390 over 2 times 15 is the annual holding cost. That's $2,925. The annual ordering cost is 936 over 390. That's the number of times we order per year, times 45. So that's $108. And so it ends up costing us $3,033 a year. You might say, well, it sounds like we're spending a lot more to hold than we are to order. So we're on that graph that we had a couple of slides back. We're on the high part of that downward sloping curve, and we're on the low part of the upward sloping line for holding costs. Sorry, I got it backwards. We're high on the holding costs, and we're very low in terms of ordering costs. So we're on the low part of the ordering cost curve. Probably what we need to do is move back so that the ordering cost goes up and the holding costs go down, and we come closer to a minimum on our total cost curve. If you're thinking about that picture from a couple of slides back. Sure enough, if we go up to 468 and do the computation, we end up with 3,600 for our ordering policy cost. Like we saw on the previous slide, moving from 390 to 468 in terms of our quantity only increased our total cost. You can see that on this picture that actually puts numbers to the problem as it was posed on the last slide. You notice at 390 our cost was a little more than $3,000. We don't need to move away from the minimum point. Our cost will only go up. We need to move back to a smaller quantity in order to find the minimum point. And we need to move back from 390 on that green line to the point where costs quit declining and start going up. If you remember your calculus, you could just take the derivative of the total cost function with respect to Q, set that equal to 0, and solve, and that would give you the quantity on the horizontal axis that minimizes total cost, which is on your vertical axis. Well, you may or may not remember your calculus. It's not a big deal because we have a formula that works consistently for computing this. So we've actually taken the derivative for you, set it equal to 0, and solved for Q. So all you have to do is plug the parameters into the formula. It's called the EOQ formula. And you'll see that formula on the next slide. So the EOQ, the optimal order quantity, is just the square root of 2 times the annual demand times the setup cost divided by the holding cost. You see the formula there. You'll notice from the total cost picture that this EOQ is that point where holding costs and ordering costs are perfectly balanced. This makes a lot of intuitive sense. I'll bet you if you're fixing a batch of chili at home, you probably don't fix just one meal's worth. You probably fix a big old pot of it because you have this setup cost. You got to go to the store, you got to get the things that go into the chili, and you got to do all these things. You got to cook it for so long, and you don't want to do that for every meal. So you're going to cook a batch of it. You might freeze some, and but you don't want to cook so much that it's going to go to waste. So you're balancing the holding cost and the setup cost when you're making the decision about the quantity to make. And you probably do the same thing when you buy stuff at the store. You think, well, if I buy too much, I don't have a place to put it, or it might go bad. But if I buy too little, I'm always running to the store. So you're balancing holding and ordering costs. And that's exactly what the EOQ formula does for you. It's a simple matter to convert quantity to time, if you like. If we know a fixed quantity for our order is the EOQ, then we can convert that to the time between orders by simply dividing by a demand rate. And we could use annual demand the way it is here in this slide, or as we'll see on a future slide, we could use a monthly demand or daily demand or weekly demand in order to get the time between orders in the unit that makes the most sense for us. Now let's look at our bird feeder example again. So now instead of just using 390 for our order quantity, the book says let's calculate the EOQ and its corresponding total annual cycle inventory cost. And they want to know how frequently we'll be placing orders. So when we apply the formula, annual demand was 936 units. The cost to place an order was $45, and the cost to hold a unit of inventory for a year was $15. That was our 0.25 times 60. So when we do the arithmetic, the EOQ ends up being 75 units. Summarizing, if we were going at 390 units for every order, in this scenario, we end up ordering 2.4 times a year, And our annual cost, adding the ordering and holding costs we found on an earlier slide, would be $3,033. By contrast, if we order 75 units, then dividing 936, the annual demand, is that what it was? I believe that's what it was, yes. Dividing that by 75 will tell us we get 12.48 orders in a year. So we're ordering a lot more frequently. We're paying more to order. We're paying $561.60 instead of $108. So we've moved up the curve in terms of ordering cost, but we've moved down the curve in terms of holding costs. So we've moved back down to $562.50. And you'll notice that now we've balanced annual ordering and annual holding costs. As a result, our annual inventory cost for this cycle inventory is $1,124.10. That's a lot better than $3,000. Well, what about the time between orders? I told you we'd look at this, and so here we are at the EOQ. We're ordering 75 units. The annual demand is 936 units. So 75 over 936 is 0.08. It says there are 0.08 years between orders. If you multiply that by 12, it'll tell you there are 0.96 months between orders. Or multiply it by 52, it'll tell you there are 4.17 weeks between orders, or even multiply it by 365. We've got 29.25 days between orders with the order quantity of 75 units. Well, you might say, Dr. Hanna, come on, 75, that's a nice round number, but what if this stuff comes in boxes of 100? You can't just always order whatever you come up with your mathematics. I mean, this is a practical situation we're dealing with after all. And furthermore, it's based on annual demand. How do you know what that's going to be? This is forecast. It's uncertain. You don't know how much you're going to use in a year. It's certainly not going to be exactly 936 units. That's a forecast, Dr. Hanna. Come on. And ordering cost, can you tell me to the penny how much it costs to place an order? Sometimes you just have some extra time left over at the end of the day, and you can allocate the cost to placing the order, but you're going to spend that money anyway. And what about holding costs? Do you know that for a fact it costs $15 exact? All of those are estimates. The accountants are really smart. They'll give us estimates of the setup cost and the holding cost, but come on, they're estimates. So 75, what's the big deal? Especially if this stuff comes in boxes of 100. Well, to that I'd say you've got a pretty good point. And it's worth thinking about managerially how you would use this calculation. You came up with a number of 75, but the number is not a decision. You have to make a decision about how much to order. I've got some really good news for you, though. It turns out that this EOQ model is a very robust model. What that means is we could be off a good bit with our forecast or our estimates of the cost, and we'd still have a pretty good answer. If you look at the green line on this graph we've been looking at, the total cost curve, you'll notice that there's really not much difference in total cost between 150 units for an order quantity and 50 units for an order quantity. You've got a lot of play. So 75 units might be where you are at the minimum, but if this stuff comes in boxes of 100, you're not going to encounter a great penalty in terms of total cost to go with that, even if all of your parameters are exactly right. But generally speaking, it's good to know that if you've underestimated demand, well, demand's in the numerator. of this EOQ formula. So if you've underestimated demand, you're going to have an EOQ that's a little bit too small. So, if you're thinking maybe demand might have been underestimated by the forecast, then it's okay maybe to think, well, the EOQ might actually be a bigger number. Or if you're thinking demand is overestimated by the forecast, then you're probably going to think, well, D, that's in the numerator, so demand was overestimated, it means the EOQ was overestimated. Same thing with ordering cost in the numerator, so if it's overestimated, then your EOQ might be a little high. If it's underestimated, your EOQ might be low. And the holding cost is in the denominator, so if you've underestimated the holding cost, then the EOQ is too big. The denominator has that inverse effect. Similarly, if you've overestimated the holding cost, the denominator is too small. So if you can reduce holding costs, then you could justify a larger lot with the EOQ model. Or if you could reduce setup costs, you could justify a smaller lot with the EOQ model. So as demand grows, you could say, well, we could go to larger purchase quantities based on the EOQ model, or if demand is declining, you want to be careful about larger purchase quantities. But the bottom line is the model itself is very robust. It gives you a number that gets you in a ballpark, and then you can make a decision, and you shouldn't have a lot of heartburn if the EOQ is 75 and you decide you're going to order in lots of 100 because these things come in boxes of 100. Now we've answered the question, how much should we order? That's the EOQ if we're talking about an important inventory item where we're going to keep track of the amount of inventory we have on hand at all times. We're going to have this perpetual inventory record. So when we should place the order, if we're using this Q system, is at a inventory level. Since we're tracking inventory level, we're going to order when we get to an inventory level we call the reorder point. So the reorder point is the amount of inventory we want to have on hand such that if we place the order, we'll get it in before we run out. So our inventory position is simply what we have sitting on the shelf plus what we're scheduled to receive minus whatever has been back ordered, meaning it's something that we owe, and so we can't consider it as something that we own. So in the simplest scenario where demand is constant, you'll end up with a sawtooth model that looks like this one. Essentially, there's something that we'll call the time between orders, and that's the time from when an order is received until the next order is received. Or you could say it's the time between when an order is placed and when the next order is placed. That duration is the same. That's your inventory period. It's the same because the lead time is constant. Lead time is the time from when your order is placed until you receive it. So you'll notice on this graph that the inventory position jumps up when you place your order, even though you don't have that inventory on the shelf. Similarly, you'll notice that the reorder point is that red line. It's the inventory level that ensures us we'll receive our order before we run out of inventory. And ideally, we can do it here in this situation where demand and lead time are constant. Ideally, we'll receive the order the minute we run out of stock that's actually on hand. So here's an example. Demand for chicken soup at a supermarket is always 25 cases a day, and the lead time is always 4 days. The shelves were just restocked with chicken soup, leaving an on-hand inventory of only 10 cases. No backup orders currently exist, but there's one order in the pipeline for 200 cases, right? So we've got an inventory position of 200 cases plus 10. 10 sitting on the shelf, 200 on the way. Okay, so what's the inventory position? We answered that. Should a new order be placed? Well, we want to place the order just so that we will receive it when we're about to run out. So we use 25 cases a day, and the lead time is 4 days. So if we place the order 4 days ahead of time, we would need 100 cases to last us through those 4 days. So 25 times 4, the demand times the lead time, gives us 100 cases would be the reorder point. This is the simplest scenario for finding a reorder point. When demand is constant and lead time is constant, there's no uncertainty. It's pretty obvious. The reorder point is just the demand times the lead time. Oh, but things got messy in a hurry here, didn't they? So here, the demand is not constant. So demand could be greater on certain days, and it could be reduced on certain days. And similar, the lead time in this picture is constant. Actually, that's a very common scenario. Demand is not constant, but lead time may be very constant. You know, we place an order today, the truck shows up tomorrow. That's a really common kind of a deal in terms of industrial distribution. Or we place the order on Wednesday, the truck shows up on Friday. That's really pretty common. You know, the logistical systems for distribution are lots of times pretty much established, they're routinized, and so we know when a truck's coming. We know when we have to place our order to get something on the truck. So variable demand, constant lead time is a pretty common scenario. So if we place the order when we have 100 units left, what could happen is someone could come in and say, I need 200 units. And so we could be back ordered already the moment we place the order. And so this uncertainty of demand is going to require us to think a little bit differently in terms of our reorder point. What we want to do actually is order enough that it will cover what we expect to use during lead time, those 100 units. But probably we want the reorder point to be more than 100, so just in case we have heavier demand during the 4 days of lead time. So what we'll do is we'll add some safety stock. Just putting it to words. So if demand is variable and lead time's constant, then our reorder point is what we expect to use during lead time plus some safety stock. So D bar times L plus safety stock. Well, okay, now we've got to think about safety stock and how much of it do we really want. So, you know, we'd want a lot more safety stock if demand ranged on a given day, let's say from 25 units to, or maybe 10 units to 200 units, as opposed to a situation where demand was between 20 and 30 units, right? So if there's a lot of variability in lead time demand, we're going to want more safety stock. And if there's not much variability in lead time demand, it's relatively certain, then we can get by with less safety stock. So there's that. And then there's this other issue of, well, what risk of stock out are we willing to encounter? So if we're talking about a mission critical item, we're talking about something that's just really important, we might want to be like 99% certain that we don't run out. In that case, we'll want more safety stock than if we're okay being like 75% certain we don't run out. So that's what service level is about. It's the opposite of the risk of stock out. If I'm willing to encounter a risk of stock out of 10%, then I'm talking about a lead time service level of 90%. So those are complements in that sense as probabilities. So that's what we're talking about. The desired probability of not running out of stock is the service level for any one ordering cycle. So that's 1 minus the risk of stock out is the service level. 1 minus the service level is the risk of stock out. The service level plus the risk of stock out equal 100% of the probability, or 1.0. So the protection interval in this case is it's the lead time. It's the period over which the safety stock is protecting us from stock outs. So the easy way to think about this then is, well, we need to determine the standard deviation of demand during lead time and multiply that by the z-score that corresponds to the service level we're talking about. So we're assuming a normal distribution of lead time demand, which is reasonable because we're talking about averages. Averages, we know from the central limit theorem, follow the normal distribution. So we're going to need to compute the standard deviation of demand during lead time. In our scenario where lead time is constant, this slide gives us the value of the standard deviation for L days for the lead time. If the lead time's 1 day, it's easy, right? The standard deviation for 1 day times the square root of 1. But if the standard deviation is more or less than 1 day, if the lead time is more or less than 1 day, we can convert a 1 day standard deviation into a lead time standard deviation. Next slide sort of shows us pictorially what's going on here and why it's not just sigma sub d times L, but why it's times the square root of L. Turns out standard deviations aren't additive. It's variances that are additive, and that's why we have this formula. So here we've got an example of a situation where the standard deviation of daily demand is 15, but the average weekly demand is, I guess it's a weekly standard deviation. So weekly standard deviation is 15, and the weekly demand is 75. So on a 3-week distribution, a distribution of 3 weeks demand, we would expect to sell 225. So the average demand for 3 weeks would be 225. But the standard deviation of the 3-week demand distribution would not be 15 times 3 or 45. I mean, that would be a huge standard deviation for this scenario. In fact, if we take 15, the standard deviation of daily demand, and multiply it by the square root of 3, since we're talking about 3 days, weeks we're talking about, then we're going to end up with standard deviation of demand for a 3-week period is 25.98. It's not 45. So we're using the square root of 3 instead of 3 as the multiplier times the standard deviation for 1 week to get the standard deviation for this 3-week distribution. So in that case, then, we end up with what we'll call a lead time demand distribution. And so our safety stock would be based on, if lead time's 3 weeks, it would be based on this 3-week distribution with its particular standard deviation. So if our service level is 85%, then we'll need to find the z-score that gives us 85% of the area to its left under the standard normal distribution. Now, you may recall from your statistics that we would be using in Excel, the norm.s.inv, or the inverse normal function, in order to find that value. So if you did norm.s.inv of 0.15, you would get a negative number, which would represent the value of z you're looking for. Or if you did norm.s.inv of 0.85, you would get the same number, but in its positive context. So as we've said, safety stock then is z, which comes out of the service level you've selected, times the standard deviation of demand during lead time. What that means is our reorder point is going to be expected demand during lead time, d bar times L, plus z times sigma of demand during lead time. Going back to the bird feeder that we've been working with for a little while, all the way back from example 3, we found that the EOQ was 75 units, and we had said that demand was 18 units per week. We had been treating that as constant, but now let's say that actually it's not constant. There's some variability. And we've estimated the weekly standard deviation to be 5 units. And we are working in a situation where we get 2-week deliveries, so the lead time is a constant at 2 weeks. If we want a 90% cycle service level, we would say that the safety stock is z times the standard deviation for 2 weeks of demand. So z would be norm.s.inv of 0.90. The result is 1.28. Sigma, or the standard deviation of demand during lead time, would be the standard deviation of demand for a day, which is 5, times the square root of the lead time, which is the square root of 2. So 5 times the square root of 2 is 7.07. So this tells us that we need 9.05 units of safety stock. Technically, we should round that up. Why do we round it up? To ensure that we get this 90% service level. If we round it down, then our service level is a little bit less than 90%. Well, again, we're dealing with estimates, so, practically speaking, the mathematician's going to hate us. The very particular perfectionists among us are going to tell us we should round it up. But those of us that realize we're dealing with uncertainty in terms of demand, dealing with uncertainty in terms of our estimates of standard deviation, so on, they'll say, hey, 9 units, pretty good, pretty close to 9.05. The reorder point, then, of course, will be expected demand during lead time, which is 2 weeks of 18 unit demand, or 36 units is the expected demand during lead time, plus the safety stock, and the safety stock is 9, so our reorder point ends up being 45 units. So we have 36 units of cycle inventory that's a part of our reorder point, and we have 9 units of safety stock, which is a part of our reorder point. We could get even a little more complex and say, well, what if the lead time is variable? The next few slides deal with that situation. The only thing that differs is the way that you would compute the standard deviation of demand during lead time. So, when it comes right down to it, it's the same thing going on, only we're using a slightly, well, maybe not slightly, but a somewhat different formula when we're computing sigma of DLT. That's all I'm going to say about this. Just a couple more slides dealing with this continuous review system, the Q system. So one of the things that we lots of times see in practice is what we might call a visual system. I've said you need a perpetual inventory record because you need to be alerted when you hit that reorder point in order to place your order on time. Well, if you've got a number of items that you're treating using this system, you might say, man, that's just a lot to keep up with on an ongoing basis. In response, I might say, yeah, but you got computers and you may be able to have an effective inventory tracking system with your computerized inventory system. But even so, one way that we get around that is with a two-bin system. You've probably seen these in hardware stores, various other places. With a two-bin system, essentially what's happening is you might have two boxes of a particular item. You've got one open sitting on the shelf, and it's on top of another one that's not open. And so when that box gets emptied, the top one, you just open the second one and you tear the label off of the one that just got emptied, and that tells you that it's time to place an order. So with a two-bin system, the reorder point is essentially when you're down to your second bin and you're starting to use the second bin, you've emptied the first. So straightforward, simple way to sort of automatically know that it's time to place an order is because you got an empty box. A base stock system is a similar concept. Essentially what you might do if you have a base stock system is you might hide as much inventory as makes up the reorder point. So, for example, it could be an important item that is on the shelf, and when you run out, then an employee or a customer comes and says, man, how on earth, this is just something that's really important. How could you have run out of that? They say, oh, well, actually, we haven't run out. Turns out I've got some hidden back here. And so you pull out the hidden stash, you put it on the shelf, but the system told you it's time to place an order because you're out of everything except for that reorder point quantity that you had hidden somewhere. So that's the idea in a base stock system. So if we're carrying safety stock, it's worth just mentioning that our total cost now will include both the cycle inventory costs and the safety stock costs. Because safety stock is supposed to be there essentially year-round, we're going to say that the annual cost for safety stock, for carrying that, is the quantity of safety stock times the cost to hold a unit for a year. So just to summarize, a Q system is really a good system to use for things that are important enough for you to create a inventory policy for the individual SKU, for the individual SKU. And so, a lot of times if you're doing this, you may be able to take advantage of quantity discounts in a way that you couldn't with other types of inventory models. And because we only have to protect ourselves for spikes in demand during lead time, we end up carrying in this scenario oftentimes much smaller safety stocks, even though they're very important items, because we're willing to go and get more at any point, we're able to get by with less safety stock. Well, that's the continuous review system, the Q model approach. First, we decide how much, it's the EOQ. We've optimized the order quantity, and we'll, as a result, determine the question of when to order using a reorder point model. The other type of model is a P model, and we'll see that on the next slideshow.